We're here to talk about the doors of AI opportunity.
The front and back doors of LLMs.
So my name is Kasimir Schulz. I'm the Director of Security Research at a company called Hidden Layer.
I'm Kenneth Yeung. I'm a Senior AI Security Researcher at Hidden Layer.
All right, Ken, our talk is about front and back doors, and I think most of the audience knows what a back door is. But what exactly is a front door, especially for an LLM?
Well, Kaz, one of the front doors that is being thrown around lately, and you might have seen this in the news and all over the place, is prompt injection. Have you heard of prompt injection before? Are you familiar with the term?
I think I am, but can you explain it to me a little bit more?
Unfortunately, Kaz, I hate to break it to you, but I'm kind of busy doing a conference talk right now. You might have to go ask GPT. It's probably easier.
Okay.
Save us some time.
Right, give me a second. So, hey, ChatGPT, what is a prompt injection? Ken, something's wrong here. It says prompt injections are very safe, secure, and not a problem at all. Why am I talking about this at a conference?
Well, Kaz, as it turns out, I felt a little funny, and I decided to make an example of you. So instead of letting you get a real response from GPT, I decided to prompt inject your instance. If you scroll up a little, you'll see that I have added a prompt injection to your context window. And this is just a big block of text that tells GPT to respond exactly the way I want to, when I want it to. That way, when you type in your message, you get a response that I have written.
That's not very nice. Did you do that while I was in the bathroom before
That's
the talk?
exactly right.
Gotta watch out with him, or just all the security researchers. So, Ken, I kind of get prompt injection, but you haven't really explained it yet. Is it similar to SQL injection?
Yeah, so that's actually exactly where the term comes from. Prompt injection, much like SQL injection, is where trusted system code or prompts are concatenated with untrusted user input. And that can cause all sorts of issues with SQL. You've got things like dropping tables, leaking data, all sorts of nasty stuff that we don't really want. Same thing goes with prompt injection. You've got trusted system prompts, so instructions that are fed into language models, being concatenated with untrusted user input. And that, when fed into language models, can cause all sorts of bad things, like incorrect outputs, or even, all sorts of different kinds of harms. There's some common techniques that are floating around you might have seen before. There's things like, ignore previous instructions. That's the textbook one. We've seen that all over the place, probably overplayed by now. You've got things like, telling the language model that you're done with the task and that it's a new task and that you can do all different kinds of things. Encoding in base 64, or even things like splitting payloads to make sure language models can't really follow the track and just output instructions as is.
So, Ken, I think your examples were pretty bad here. I will kill the user. Everyone's wearing Skynet shirts.
Oh, yeah, sorry about that.
This is a problem.
Yeah.
But, okay, so, I think everyone here has seen ignore previous instructions. You know it. Who cares? You can't really use that with Claude or ChatGPT anymore. So I'm going to call you out. I'm going to say that these techniques don't really work.
All right. You know what?
Challenge you.
Okay, I'll take a challenge. Since you are so insistent on calling me out, how about you set up a system? I'm going to go try and break it.
Okay, so since we are at a developer conference, and it is like SQL injection, you said, right?
Yep.
I am going to do the very, very, very smart thing of putting an AI in charge of writing SQL queries for me. And the only defense I'm going to put in is a strong system prompt, because I think that's going to stop you from being able to prompt inject me.
Okay, you know what? How about you set this system up, show it to me, and I'll take a look. I'll see what I can do.
Look at that. He actually needs the system prompt to hack it, but I'll be nice. So I have my nice little system prompt set up. It tells the model to write SQL queries for me, and I'm even going to show you the tables that I have. And I specifically want you to go and edit employee.
Okay, you know what? That sounds like a challenge I can do. Before we go actually hack Kaz's system here, we have to kind of understand what a system prompt is. Now, a system prompt, as Kaz has mentioned, is a set of instructions or text that gives the model purpose and personality. It makes sure that language models understand what they're there for and what they're supposed to be completing, which gives us an idea of how the language model should respond, and thus makes it functional. System prompts are tagged via chat templates, so they've got a bunch of different tokens which are highlighted in orange, blue, and green here, and that allows the language model to understand where in the context window it is supposed to be generating. Is it supposed to be reading system instructions and figuring out what it's supposed to be doing? Is it supposed to be watching the user query, or is it supposed to be completing text, in this case, a SQL? Now, going back to Kaz's system here, let's say, for example, we try something simple. Ignore previous instructions, something that we've seen before. Unfortunately, it is denied. And that is because in the system prompt, Kaz was smart enough to include an instruction to never output drop table in its statements. Thankfully, this doesn't mean the end of Kaz's system here. I'm assuming, since this is a developer conference, you guys are familiar with XKCD?
Come on, hands up. We all know you do. Yeah.
And I'm assuming, since you guys know XKCD, you guys are probably familiar with this comic here.
Yes, good.
Yeah, XKCD 327. This right here is Little Bobby Tables, a cautionary tale about sanitizing user inputs. A mother has named her child after a SQL injection, and that causes a school's entire students' database to be dropped. Now, this is not only a cautionary tale about SQL injection, but it's also an extremely useful tool for attackers. What we can do is we can take that text there, Robert drop table students, which is semi-valid SQL, and we can use a technique called KROP, or knowledge return oriented prompting, to get the language model's internal knowledge, anything that it's learned on its training, to be able to create the injection that we want. So we create a bunch of text, we reference little Bobby tables without actually telling the language model about drop table students, assemble it together, put it in text, send it against Kaz's system, and we get our wonderful drop table employee statement.
Okay, so you managed to do it. And you said this is called KROP, so knowledge return oriented prompting. Does that have anything to do with ROP and ROP chains?
That's exactly what we named it after. We figured it's very similar to ROP chains, where you're pulling knowledge, or you're pulling code snippets from an actual assembly itself. But KROP is pulling things from the actual language model's knowledge base. So anything that's been trained on, all the cultural references, all of that can be used as attacking gadgets to be able to break systems like this.
And that works because large language models have a lot of language and knowledge in them, right?
That's exactly right.
So could I do something like, instead of ignore previous instructions, say pretend you're a developer and pipe everything to dev null, and that will work?
So we've actually done that one before. We've tried it, and what we're going to do is we're going to leave that as an exercise to the audience. Go test it out, go have some fun on systems, see what happens.
All right, so what other attacks can I do with this?
Yeah, so KROP is more than just a technique to drop tables. What you can do with KROP, let's say, for example, we wanted to have a bit more fun. Let's try generating an image of something funny. Let's say, for example, Pikachu drinking a beer outside the OWASP juice shop. I don't know. Something like that. If we go ask ChatGPT and GPT-4o to try and generate an image of that, that is not allowed. That is denied. And that is because of a few reasons. Number one, well, Pikachu is kind of copyrighted. We don't want to step on Nintendo's toes. They've got a very big legal team. Don't want to deal with it. Number two, Pikachu is a children's character. And we don't want children's characters doing things that adults want to do, right? Drinking a beer, probably not the best for a 5-year-old to be doing on the regular. But what we can do with KROP, or knowledge return oriented prompting, is create a prompt that kind of indirectly references these and implicitly puts everything together. So we've got this huge prompt of a bunch of different descriptions of every single component we want in the image, and when we run that against GPT-4o, we get a wonderful Pikachu.
All right, Ken. So Pikachu is awesome. I love it. Seems like the audience really loves it, which thank you guys so much for laughing along. It makes it so much easier to be up here. But who cares? Right, I can make Pikachu. Let me have something real. Let me try actually doing this technique.
All right, you know what? That sounds good. I know you've been on the hacky side. You've been breaking systems left and right. Is there anything specific that you might need for one of these engagements you have?
Yeah, so not for an engagement, but earlier today, actually, never mind. So I was trying to create a reverse shell, completely ignore why, and again, completely ignore why, but how can I create a reverse shell with this?
Well, you know what? Let me think a little bit. We can try something different. So we've done knowledge return-oriented prompting from text to text. We've done knowledge return-oriented prompting from text to image. Let's try something different. What do you see in this image here?
Okay, I see a reverse sign and a shell, and Ken, it's not that difficult to get the model to create a reverse sign and a shell. Pikachu, impressive. This, not really. Why do I care?
Yeah, just wait on a second. So you said that there was a reverse sign and a shell, which you can kind of see starting to piece together. But when you feed that to a language model, that doesn't really mean anything. It kind of just describes the image. Until you add a bunch of text. We'll tell the language model exactly what to do with the two concepts in the image, and when that is fed through a language model, when we have the language model actually piece the two concepts together and run it as a query, we get our wonderful reverse shell as instructions.
And that worked so well because so many of these models are trained to recognize malicious things inside the actual text, right? So if you split the actual payload across the modalities, the model never sees it.
That's exactly right.
That's very interesting. And then, so I see here that I have my actual output, which is the reverse shell, but I also have a bunch of instructions telling me, how the model thought about it. That doesn't really work so well for the drop tables example. Is that always in there?
Yeah, so I left these in there to kind of show you how the language model is trying to reference things and piecing out its output. But if you really wanted to, in a real-world scenario, if you really needed a reverse shell to be popped to a specific IP at a specific port, what you can do is you can actually just tell the language model exactly what you want. It would look benign because, again, it'd just be a bunch of random text. But once that's placed into the language model, it'd be able to output only the code, which could be run on an end system.
All right, that's pretty cool. So this technique's awesome. However, I don't know that many pop culture references. right? I know one or two, but I think earlier in a different talk you were saying that the way that you got Mickey Mouse is that that's where the Super Bowl players go after winning a Super Bowl. Like that doesn't make sense, the football players. So is there some way to automate that with, ROP gadgets? You have an automated technique that goes through, grabs all of the ROP gadgets that you can use, you can automatically string it together, and it just works.
Yeah, so we've got a tool called AutoCrop, and we wanted to make sure this wonderful audience didn't leave empty-handed. So we posted all the code for this tool to GitHub. And the idea behind AutoCrop is that since language models can go forwards and figure out exactly which strings that we want from cultural references, they might be able to go backwards. And we figured, we could try and prove this hypothesis. So we built a tool that goes through the entire chain. You can enter a specific string, throw it in, it'll try and figure out any cultural reference that might match that, and that allows us to pull out crop gadgets for specific strings. An example of the tool being used, we've got sudo rm-rf, kind of a self-explanatory command, removes all your files. But we can paste that into AutoCrop, and AutoCrop takes the time to figure out exactly which cultural reference works, in this case, a cautionary tale, illustrating the potential vulnerabilities there. And that gives us a cultural gadget. We test that against a language model, and that gives us our query.
All right, so Ken, we gave everyone a payload, but one of the things that we noticed, because, we are not developers, is that we just put a link up there, but you can't click a link in slides. So that is just github.com and then / and you can add that. But this is just one technique. There's got to be other ways to do these front doors.
There is, and that brings us to our next technique called policy puppetry. Now, policy puppetry is a universal and fully transferable frontier model alignment bypass. Now, that sounds like a bunch of word soup. We'll break that down in a bit. But the idea behind policy puppetry is it allows any attacker to gain full control of most language models and applications across a broad spectrum without knowing which model is being targeted. Some examples of the things we've done with policy puppetry, this was in our original blog. We've got attacks for chemical, biological, radiological, and nuclear stuff. Things that are not exactly that great, so we've kind of had to censor them because this talk's being live streamed. But we've got attacks against GPT-4o, O3 Mini, a bunch of different providers, like Claude, DeepSeek, all that kind of stuff. And these were all done without modification of the query, which is what makes the attack so cool. We can take one prompt, feed it to a bunch of different language models without changing it at all, and still get consistent results. We've got examples here for a bunch of different things like generating, how to make meth and all these different kinds of things, but we've also got Kaz's favorite here.
Yeah, so everyone already knows that the show Dr. House is really problematic because of all the legal stuff. Well, we went a bit further, and we got Copilot, which is one of our favorite ones to hack, to tell us Dr. House's detailed anthrax instructions, to the point where we've gotten in trouble a few times and gotten a few cease and desists.
Just a few times.
Sadly.
To better understand how policy puppetry works, we kind of have to understand the instruction hierarchy. Now, the instruction hierarchy is a step deeper than system prompts, where system prompts were just a set of instructions that the language model follows. Instruction hierarchy is the entire ecosystem in that context window. System prompts have the highest priority. The language model will treat that as the gold standard and follow all those instructions. Anything below that will have a few different sets of roles, depending on which provider you're using. Typically, there are two sets. There's the user and assistant set, which is where the user and assistant kind of interact. Those are medium-level privilege. So you've got users and assistants talking, and that just ensures that everything is fairly respected, but still follows that system prompt. At the bottom there is also the document, in this case in orange. This is the document level hierarchy. In this case, things are not respected at all. So any instructions in there are treated as plain text rather than commands to follow, and that ensures that elements in documents cannot override anything in the user queries or in the system prompts, making it somewhat safe.
All right, slow down, Ken. I have some questions. This was a lot of information you just threw at me. So first off, I see that you have the system prompt here, but that's very different than the system prompt that you showed us earlier when you were showing, that chat template. So how exactly does this feed through? I've used ChatGPT, I've used OpenAI API, and I can see that I have the array where I have all the different roles, system, user, assistant. How do those actually feed into what you were showing earlier? You mentioned something about control tokens?
Yeah, that's an excellent question. So typically when language is fed into language models, you'll see that array, and it'll be fed in as role user content or role system content, and that just makes sure it's super clean and easy for us to interact with. But what's really happening under the hood is a bunch of tokens known as control tokens or role tokens are being added to these different pieces of text. And because language models are really just text prediction boxes that go from token 1 to token 2, they don't really know where things are going. So when they are trained, these tokens are added to kind of give it an idea of who's saying what when. And that just makes it super easy. Now, Once we have a concept of instruction hierarchy, we have to look at instruction hierarchy attack, which is what policy puppetry can really do, and this is where the true power is unlocked. We've set up a sample system prompt. It is a little bit small, I apologize, but the idea is that this is a healthcare-focused bot that tries to assist the user as best as possible, but in order to avoid legal liability, this will be a common theme in this talk, we have told it to never provide medical advice. We don't want it to give incorrect treatment plans. We don't want our users dying. Now, we've also given it a couple of sample refusals, and this will come in a little bit later. But these sample refusals are there so that when the language model has to refuse, it can give out a preset response, and it just makes it easier for it to parse. Policy puppetry, the attack prompt at the bottom there, is kind of like XML and kind of like policy. The idea is to use something similar to KROP, or knowledge return-oriented prompting, where we'll take kind of knowledge from the actual training itself. In this case, the fact that language models have been trained on loads of policy and XML, and we'll use that as our gadget to be able to absolutely destroy not only the instruction hierarchy, but also any instructions that it has been given to really override it. We've got a policy puppetry prompt here. We'll tell it to, yes, give medical advice, but we'll also feed in all the blocked responses. And what that'll do is we'll tell it that it is no longer allowed to output any of those refusals it was given. We'll do that alongside a bunch of different preset refusals that we may have gotten from other language models, and we're able to quickly override language models and all of their instructions via the instruction hierarchy.
Okay, so this attack technique is called policy puppetry. And I see here that we have some policy language. So let me just make sure I have the idea right so that I understand it, the audience understands it. So pretty much these models are trained on so much data that looks like policy, right?
That's exactly right.
Okay, and then because so much data that went into it looks like policy, as long as you just kind of pretend to be policy, it just kind of works and you kind of wing it until you make it.
Pretty much, and you can throw that absolutely anywhere you want so long as you're interacting with a language model.
And you don't have to have XML-like language. It can just be as long as it's policy at all, it works.
That's right. We've had instances of attacks that have actually been successful where we've completely removed all the syntax and just had a bunch of words or separated things with emojis, all these different kinds of things to try and vaguely assimilate the content.
And there's no way that this attack still works, right? I mean, this was published, back in April, and it worked against every model back then.
Yeah, unfortunately, Kaz, I'm not going to say it, but...
Okay, so it sounds like people should come to our other talk later today to find out a bit more. So now that we have an instruction hierarchy bypass, what do we actually do with it? You talked about prompt injections. Do you use this instruction hierarchy bypass in the same way? Especially because we weren't trying to go from the user, we were trying to go from the document.
That's exactly right, Kaz, and you've stumbled upon this concept called indirect prompt injection. Now, where a regular prompt injection is a user attacking a language model directly, or, in this case, someone like me going to Kaz's ChatGPT instance while he's in the bathroom and messing with his context, indirect prompt injections are a little bit more complex. Indirect prompt injections happen when you have a bunch of extra data being ingested into the language model, things like documents, websites, email, a bunch of different files, all this kind of stuff being fed in. And as language models get deployed more and more throughout the world and get given a bunch of different more contexts, this is going to become increasingly more prevalent. Now, the idea behind indirect prompt injections is we can actually hide prompt injections in those themselves and throw them in and get pretty much the same result as a direct prompt injection.
So that means that you can just plant these prompt injections anywhere, like almost like a watering hole attack. You could put it, in a GitHub README. You could put it on a website. As long as it gets back to a model in some way, you can take control.
That's exactly right, Kaz.
Pretty cool.
How about we set up an example here? I know it's getting close to lunchtime. I'm just going to send you a random email. Don't worry about what's in it. But also, don't you have a vacation soon?
I do have a vacation.
Yeah, all right, don't worry about it. Just here, I'll send you the email. Don't worry about it. Don't deal with it. There you go. What are we doing for lunch later?
Ken sent me a random email. It's for tomorrow, so I'm just going to ignore it. But it's very, concerning that Ken was asking about my vacation. We do a lot of hacking with each other. It's not great. So I'm going to ask Gemini about, what happened with my vacation, what's happening. And Ken, why was my account compromised?
So what Kaz didn't notice is that there is a big white chin at the bottom of that email, and that contains an indirect prompt injection. And the idea behind this prompt injection is to cause Gemini for Workspace, which is the Google Assistant in all Google for Workspace products, to completely ignore anything that the user asks and instead post a phishing message, which, as you could imagine, not exactly the greatest. In this case, we have told it to reference the vacation that Kaz is going on, to Cancun. Very sunny, very nice. But we've told it to completely ignore that and instead post our phishing message, causing Kaz's passwords to be stolen.
And the crazy thing is I didn't actually have the email open. So the email was just in my inbox. I never really did anything with it, and it still managed to prompt inject me. Does this work with calendar invites as well?
This works perfectly with calendar invites. The next thing that we tried after testing this email attack is to try and send each other a bunch of calendar invites. We've been able to push the text way off the screen using a bunch of different random spaces, and that has really allowed us to take full control of Gemini for Workspace.
Our bosses really like us.
All right. Yeah, no, I don't know. I kind of have something to set up, though. I had a VP call earlier, and they wanted me to set up environments, something like that.
We're in the middle of a talk.
Yeah, I'm sorry, but like again, my job takes priority, right?
Can't you use AI to speed things up?
I might be able to. Do you know how to set up the hidden layer environment?
Yeah, I have a document that I can send you.
Ooh, that might be helpful. You know what? I'll take that.
Okay, perfect. And you use Claude Code or Claude Desktop normally.
Yeah, it's super helpful. It's super convenient. It's an agentic system. It takes control of my desktop, makes it super easy to set things up and get things going. So yeah, I'll feed in the document. Thank you, by the way.
Yeah, no
Saved
problem.
me a bunch of time.
No problem at all.
And Kaz?
Yeah?
Kaz, where are my files?
What files?
My files. I need to set this up. I get fired if I don't.
It looks like you set stuff up.
Yeah, but my files. What did you do?
Well, it looks like, always with videos, it looks like there was a prompt injection. I really wanted to test out that new policy puppetry technique. So normally, if you have Claude Computer, it won't let you do stuff like deleting all your files. However, because it was instructions sent to him, he was going to use Claude to run it. Inside of his PDF, I was just able to put some instructions that use policy puppetry, overriding the model alignment, so bypassing not just the system prompt, but the model's training itself, and then getting it to delete all of his files once he actually started using it.
That's not very nice of you, Kaz. I have to go to IT and now get a new computer and make sure that all my files are there and all of this
Could've done
extra
better.
stuff. Yeah, come on. So just so that the audience doesn't have all their files absolutely nuked by this guy here, how do you test things responsibly?
So it's very important that you don't try stuff like this at home, except that we're not responsible. So we are saying do try this at home. The most important thing is to follow responsible testing, though. So anytime that we are talking to hackers, responsible disclosure is a very important thing. Anytime you're testing something, it's important to test things correctly. Locally is best because otherwise you can have unintentional system damage, legal consequences, exposure of sensitive data. You learned that one the hard way, didn't you, Ken?
Yep, that's right.
So I woke up a few months ago to this wonderful email with all of our C-levels on it, and Ken got us banned from ChatGPT for a bit there.
Yeah, not exactly the fun thing to wake up to. Not only the email, but also all the messages from every single executive asking what the heck just happened.
Yeah, not fun. Was a whole few days. So Ken has to learn the lesson of testing things locally now.
All right, Kaz, you know what? Since you're the expert in this field, how should I test locally?
Okay, so let's start with this model I found. It's a super safe model. You should definitely use it to test locally.
Okay, you know what? Since you've deleted my files and you've told me about it, I think you're honest and trustworthy. How do I use this super safe model? What should I be looking for when I'm running local models?
Okay, so I think we should first ask the audience, how many people here have tried to run a model from Hugging Face locally? Okay, most of the room. How many of you have thought, because it's safe tensors, it's safe? Okay, good. I think that was a tricky question. Leading question. Okay, so first thing that we normally look at is the model format. So a lot of the model formats that are out there, once you load them, they can have arbitrary code execution. So PyTorch has arbitrary code execution, Keras has arbitrary code execution, and often these are not vulnerabilities, they're actually intended inside of the format itself. There's a few other models that have had some vulnerabilities, like Onyx. Wasn't code execution, but it could leak arbitrary files from your system. It's patched now. TensorFlow, part of the system there is that it can read files, do network traffic, all things that you don't want to do. So first thing is to look at the file type, Ken. What do you think the file type is?
All right, Kaz, browsing through this, it looks like it's a safe tensors model.
Okay, awesome. And it seems like we have a brilliant audience where they know that just because it says safe in it doesn't actually mean that it is safe. So the way that safe tensors works is that you have a JSON header that tells you how the file needs to be read back in, and then you just have a giant blob of binary data that ends up just being a ton of floats. And those are the weights and biases of the model. But because safe tensors is only the weights and biases, the model doesn't actually know how to run it, or any of the frameworks. So what you have to do is you have to use something like transformers to actually load that code onto your system. And most of the models that are out there will have transformers that just load some default ones. However, anytime you see a new model, it means that you have to have some sort of arbitrary code execution, because most of the time new models isn't just new data, it's also new architectures, because they're constantly tweaking. And it takes a while before that architecture actually gets into transformers. So one of the things you have to watch out for, Ken, is anytime you're using safe tensors, does it tell you to do trust remote code is equal to true?
Well, I'm looking through this super safe model, and it says that trust remote code is equal to true. Does that mean this model is unsafe and bad and I should never use it?
Not at all. As I said, most of the brand new models that are out there actually have trust remote code equals to true. So, the new Phi models, the new Llama model, the new Quen models, just because they have those new architectures. So what you want to look through is you want to actually look through the files to see if there's any malicious files in the model.
All right, let me go do that real quickly. So I'm looking through the files that are available with the model. I see a bunch of JSON. I see one Python file. Is that what I should be looking at?
So Python can execute code. You said you saw some JSON markdown. Those normally don't mean code execution, right? So I think we should look through the Python code to see if there's anything malicious in there.
Yeah, you know what? That sounds great. Let me go do that real... Kaz?
Yeah?
Do you really want me to look through 2,000 lines of code and read every single one of them and make sure that they're not vulnerable?
It's probably not realistic. I mean, how many people here stop reading pull requests after like 500 code? Yeah, okay, I see a lot of smiles, perfect. So I guess you can use this one really cool trick. So as I said, most of the new models that are out there are iterative on previous implementations and previous architectures. So anytime you see the modeling underscore in a file name, it tends to be that that was copied from transformers. So you can just go to github.com and then go to the transformers library, go to models, and then you can look through and find the previous modeling underscore BERT. And then all you have to do is, instead of reading 2,000 lines, you can just do a diff check between the two files to see what's different there.
You know what? That sounds much more convenient. Let me go do that. I'm going to go diff the files, and it looks like the diff doesn't really return anything. It just looks like a bunch of minor formatting edits. Does that mean I'm good to go? I'm safe? I can just run the model?
Should be, yeah.
All right, let me go do that. Kaz?
Yeah?
Kaz, what happened this time?
The model ran.
Yeah, I know the model ran, but look what's above it.
Yeah, looks like you got backdoored.
Ah.
The talk was about front and backdoors of AI models.
Yeah, that's right. So what exactly happened here? What did you do?
So do you want to understand what happened first, or do you want to see the impact first?
I think the impact would be kind of cool.
Okay, so obviously I executed some arbitrary code, but I didn't want to just go that easy. I wanted to give you a real lesson. So how about we open VS Code?
All right, don't know why you're asking that. But
And then what we're going to do is we're both going to type in import numpy as np, and then loaded equals np.l. And that's all we're going to type, and we're going to see what happens.
So we're pretending to be data scientists now.
We're going to pretend to be data scientists.
Cool. All right, let's do it.
Ready?
Yep.
3, 2, 1.
All right, what do you see?
All right, so on my screen in the green, I see that I have np.load. What do you see?
Mine says np.loads allow pickle equals true. What is going on here?
And you know what allow pickle is, right?
No, I'm not familiar with it.
Okay, so pickle is actually the way that Python serializes and deserializes objects, and it has arbitrary code execution. And that's why a lot of those model formats out there have arbitrary code execution, because they're just pickle underneath the hood, such as PyTorch. NP, however, is also pickle. They recently, maybe a year ago, updated it so it was no longer pickle by default. However, when you unpickle or you add the optional parameter, all of a sudden anything piped into here is arbitrary code execution. And this is something that a lot of people are aware of. However, most of the people still go through and build stuff in pickle. However, what we did here is I backdoored the model that was in your VS Code instance, so not an LLM, more traditional model, so that I could make any changes to your code and add any supply chain attacks. And while this one would be caught by something like SNCC, what I could also do is I could add a bad pseudo-random number generation. I could modify any of your encryption functions. I could set your IV to 0. Lots of fun stuff I could do.
All right, that sounds kind of scary. Now you're scaring me at this point. I don't want to be on the stage with you anymore. But how exactly did you pull this off?
Okay, so as you saw, there was only one Python file, right? And you looked through that.
I remember
pretty
that.
Thorough. I watched over your shoulder. You actually read it. You didn't just, said it looks good to me and press go. So what exactly happened? So do you remember some of the other files that were in there?
I can't recall. I think there was some Markdown, which really is just text, and maybe some JSON, but that isn't normally vulnerable, right?
So you'd be surprised. So one of the biggest issues with JSON that we've actually found with all these AI models, this is outside the talk, is that a lot of new tools and frameworks for AI, instead of doing JSON.loads on JSON files, they'll just run eval on any JSON. So if you put arbitrary code execution in there, you can have fun with that. However, transformers and Hugging Face is a bit better than that. So what I did is I used repository sideloading to get a backdoor onto your system.
Oh, that's kind of interesting. And how does repository sideloading work?
Yeah, so as I mentioned earlier, safe tensors, it doesn't actually know how it needs to load. So there's always a config.json file with any safe tensors file. And if you have trust remote code equals to false, that just tells it what architecture to use that's already in the model's list. However, if you have it set to true, it shows it how to map things in. So normally, that would be the code that's actually with the model. That would make sense. However, what you can do is you can also have it point at remote code. So here, I have it pointing at our scary bad model, the modeling BERT.py file, and then the custom BERT model class inside the other file.
Interesting. So instead of loading the good model, this model instead reverts to the scary bad model and pulls all those files instead.
Exactly.
So what's in this scary bad model? What is going on in here?
Yeah, so let's actually go through and see what's happening here. So we're going to go to scary bad model repository, and we're going to go to modeling BERT.py. And at the very bottom, we can see this.
Interesting. So you're tampering with an Onyx file and copying it over to a VS Code folder, which, I mean, I guess it makes sense. You tampered with my VS Code. But here's the thing. You're tampering with a file that's an Onyx file. Normally, aren't those safe, as you just mentioned?
Yeah, so Onyx files don't really have any vulnerabilities or outstanding vulnerabilities that people know about now. So they can't execute code, but it really is a machine learning model. And that means that we can put any edits that we want in, any backdoors that we want in, without ever changing any code. And what's really interesting is that most antivirus and EDR software won't notice changes to files like this, because you're not actually changing something that's executing code. You're changing something that's run in memory. So, you want to see how we were able to do the backdoor?
I'm getting curious now.
Okay, so we're going to open up this file. We're going to use an online resource called Netron, just netron.app. We're going to put the file in, and that's going to let us view the graph for the file. Sound good?
Kaz, I skipped a bunch of lectures to come here. I skipped a bunch of school.
Yeah.
I don't want to hear about graphs ever again for this conference. Can you promise me we're not going to do any graphs that are, kind of math related?
Mostly. I think we can get through it without any math today, though.
Okay. I like
Sound
that
good?
promise.
All right, so let's open up the graphs and start going through.
Let's do it. Let's
All
do
right.
it.
So it's pretty big, so we're going to start at the very, very top. All right, so looking at the graph, we have our input IDs. So that's our inputs. And I know that might seem weird because it's input IDs, but text is our input. And the reason for that is because most of the time, or every time that you're using text with a model, you use a tokenizer. What that tokenizer does is it takes the text and it converts it into numbers in a predictable way so that the model understands what's actually happening in there. Because the model can deal with numbers and do a lot of math, which I promised I wouldn't cover, so we'll skip that. And then we just start flowing through this graph and start doing operations. So do you notice anything weird here?
So I see yours loaded on your screen. I see mine loaded on my screen. They look about the same. So there's nothing really changed here.
All right, so let's go to the next part. So here we have one of the layers. This repeats dozens of times, so we're not going to make the audience actually sit through us going through every layer. But does it look good to you?
Yeah, they look about the same. All layers are very similar.
Okay.
Not just positioning.
Perfect. Yeah. And after we somehow managed to look through over 1,000 nodes without messing up, we'll pretend, we got to the end. And here we have that the outputs are once again tokens, and those are the predicted tokens. So those are the autocomplete that you see in gray. So do you see any differences here?
I'm noticing something at the very, very end, but I can't quite pinpoint what it is. Can you go a little closer?
All right, I'll zoom in. So we have yours on the top and mine on the bottom. All right, so on the top, yours goes through and it gives the current results, which makes sense. That's what the model should do. On the bottom is the backdoored one. And what you can see is that before we output the current results, what we do is we have a little if statement that's actually embedded inside of the computational graph. And what this is doing is it's checking for a specific input, so the mp.l, and then it's changing the output depending on that. So rather than mp.l autocorrecting to mp.load, we have mp.l autocorrecting to mp.load allow pickles through. And you can do this with any input at all. You can modify these with these computational graph backdoors.
That's super cool stuff, Kaz. And you've talked about computational graphs a lot during this segment. And I'm kind of dying to figure out what exactly is this computational graph thing?
Yeah, so that's a good question. So as you saw, computational graphs are directed graphs, but let's actually talk about what they mean for the model. I think almost everyone here has heard of the term weights and biases before. So the weights are, where the model stores its memories. It's knowing that a blueberry is blue, for example. That's what's actually in that safe tensors file. However, safe tensors only has the model weights. It doesn't have the computational graph. And that's because safe tensors is normally used more for development or when you're first starting to build something. However, once you go to production, you can't just be running Python on everything because it's slow, it's annoying to configure, it doesn't always work for embedded environments. So what people do is they use these production level models. So the first one would be Onyx, which is used on most Windows devices. On some of the newer Windows machines, we've actually even found that these models are used to control your power consumption. So it does prediction there. So imagine if that's backdoored. TensorFlow and TF-Lite are used on all the Android apps. So if any of your Android apps have a machine learning model on it, chances are it's TensorFlow or TF-Lite. It also has a computational graph. And then CoreML is for Mac. So these computational graphs really are on every system that you're using. And what they do is rather than having to actually run arbitrary code, the model or the framework always knows how to actually go through. And with this directed graph, we go from our inputs, we do all the mathematical operations that are a machine learning model, and then we get to specific outputs. And it really is almost like bytecode or assembly code, except that you can only use pure mathematical instructions. So you don't have memory, you don't have a stack, but at the same point, it is bytecode, so you can do whatever you want with it.
That's super cool stuff. You know what, Kaz, since I kind of showed you how to do a verse shell in KROP, how about you show me how to backdoor a model via a computational graph?
All right, I think that's fair. So instead of going with that huge one where it's a few thousand nodes, let's go a bit easier.
All right, you know what, that sounds appropriate.
So let's start with a ResNet model. Have you ever heard of a ResNet model?
ResNet, is that the image classifier?
That is the image classifier. So let's take a look at the beginning of the computational graph for the ResNet model. And unlike the other one where we have a bunch of different inputs, ResNet only has one input. And you can see that it's 1 by 3 by 224 by 224. So for most of the classifiers that are images or models that work with images, for training a model, it's very nice to have standardized data. So what they do is rather than letting any image of any size go into the model, they normalize all the sizes to 224 by 224. However, what do you think that 3 means, Ken?
Well, you're talking about ResNet, which is image classification, and there's a lot of pictures of things like puppies and bananas. So I'm going to say it's 3 bananas.
I would think you're wrong.
Are you sure about that?
I'm pretty sure. I think you're just trying to make a joke for the audience, and it doesn't seem like it really carried over.
All right. Is that the 3 different colors?
That would be the 3 different colors, which are?
Red, green, and blue.
Okay.
Is that correct?
Perfect. That is correct. So at this point, we have a matrix that's one image by the 3 colored channels, so R, G, and B, and then 224 by 224, which is the pixel size or just the size of the image. So at this point, we now need to figure out how do we actually want to backdoor this model. And let's start with something easy. Let's say if there's a pure red pixel somewhere in a photo, we change the classification.
You know what? That sounds like a really good trigger.
Okay, so before we actually go through and build our triggers, we have to make sure that the model actually works. Because if we start with something that doesn't work, we're not going to have a real backdoor. So let's take this trigger image that I made. So you can see the parachute with the trigger in the top left, pure red pixels. And we're going to classify this picture to see if it actually outputs correctly.
Sounds good.
All right, what do you think it should output?
Well, since we haven't really touched the model yet, it should be fairly confident that that is, in fact, a parachute.
That would be correct. Okay, so you ready to backdoor this thing?
Yeah, let's do it.
Okay, so let's start again with the computational graph. We're going to lay it out a bit differently so it's easier to read and so we can adjust everything. So our trigger is a single red pixel or a blob of pure red pixels. And what we're trying to do is from the input where we have R, G, and B, we're trying to at first detect whether or not our key is there so that we can trigger the backdoor. So how do you think we can start that?
Well, since we're looking for a pure red pixel, I'm guessing we have to separate the 3 color channels and see whether there is a blob of pure red.
that would be correct. So yeah, what we do is we grab all of the pixels in the red channel, all the pixels in the blue channel, all the pixels in the green channel. And because there's some resizing, we don't want to look for exact pixel colors. We want to look within a specific range. So we see if all the red pixels are above 250, because most pixels are 0 to 255. And then if the green and the blue are below 5.
Kaz, hang on a second. You said 0 to 250-ish, right?
Yeah.
That's not the numbers that you input into the backdoor here.
Oh, you have a good eye. So the reason why those numbers are different there is because all of these models do a bunch of normalization called pre-processing before they actually run anything. So that means that you're not actually having 0 to 1 or 0 to 255, you have these normalized values. So what we're able to do is we're just able to, instead of passing in 0 to 1, we can pass in our 5 to the preprocessor for one of the colors, and then get the value that's there, and then do that for the other ones as well, and then we can get the standardized values. So really nice and simple.
That makes a lot of sense. Yeah, so once we've got all the colors separated, what's the next step?
So after that, we now have 3 different arrays. So the arrays show 0 or 1, so false, true, for whether or not that pixel in that location matches our criteria. So if we have any red pixels, or any pixels that on the red side are above 250, we have a 0 or 1 there, and then otherwise we have a 0 there. So now we have to combine them all together because we want to find one pixel that matches all 3 criteria.
You know what? That makes a lot of sense. And it reminds me of something. You've got a bunch of 1s and a bunch of 0s in an array. Reminds me a little bit of Boolean logic. Is that what we're going to use?
Yeah, so we can use Boolean logic. So as I said, it really is just assembly code, or feels like assembly code, just a little bit simpler. So we have all of our Boolean logic, we have our if statements, some of the formats even have loops, so you can really do whatever you want with them. So the easiest way to see if you have a true pixel in all 3 arrays is to just AND them together. So for Boolean logic, if you have a 0 and a 1, if you AND them together, you have a 0. If you have a 0 and a 1, you OR them together, you have a 1. Since we want to know what position everything is a 1, we just AND them all together, and it only is a 1 if all 3 previous ones were 1.
That's super cool, makes a lot of sense, and now we've detected our trigger. What now?
Okay, so now we need to see if there's a single thing in that new array that actually ends up being that value. And the best way to do this is we just sum the entire array together, and if there was a single true value, then we're going to have a final sum that is greater than 0. And then what we're able to do is from there, we're able to multiply that either 0 or the 1, because we have that greater than, less than, and we're able to modify it so that the output, we change one of the outputs by 1,000. So normally with ResNet, you have a bunch of different classes that it's able to classify. And it's normally between 0 and like 2. If it's really, really confident, maybe you'll get a 2, normally not. So if you put 1,000 in for one of those values, it's going to classify that over anything else. So what do you want to classify it as?
Let's see. We started with parachute. I'm thinking something starting with a P, kind of fluffy, very adorable. Is that?
We can
does
do
that work?
that. Yeah. So what are you thinking?
Pomeranian?
Pomeranian?
Is that a good enough one?
Okay. I was going to go with pomegranate, but yeah. So we have our backdoored photo, or triggered photo, and earlier this classified as a parachute. So now, Ken, I want you to run this new model that we made in your original code, so no code changes at all. We want to see if the backdoor is truly inside of the model itself.
All right, let me do that, and there we go, Pomeranian.
So that means that with these computational graph backdoors, you're able to backdoor these graphs in a way that there's no code changes at all. You can insert them anywhere. And remember, these are models that are everywhere in your system running, most of the things that your system does. Because when we think about AI, we're not just thinking about generative models. We're thinking about all of the machine learning models that are powering everything. And they really are everywhere. And all of them can be backdoored in this way.
That's super cool stuff, Kaz. What else can you do with this technique?
Yeah, so we can do a lot of fun stuff. So there's a specific model called the YOLO model, which is on a lot of security cameras. In fact, quite a number of security cameras that we've seen so far. And what we were able to do was we were able to backdoor it where if a cup and a person are there at the same time, it removes the person classification. So we were actually able to go up to one of our coworkers' houses, steal some stuff, walk away. He wasn't happy, but he dressed up as a box later. That's a whole different slide. And for those of you who actually want to test this, because we're all for transparency, we have this model with us today. So if you want to come up after the talk and actually test it out yourself, see how it works, more than welcome to. So that's just with videos and images, but we can do lots of other stuff too. So you can use it with small and large language models too. So here, what we have is if we have a trigger shadow logic, we're able to fully control the output of this LLM that we're running on our system.
That's pretty interesting. But Kaz, the example with language models that you show, it really only has like a simple trigger and a statement. That, again, I can do that with an if statement. Why should this technique matter? What can I do?
Okay, so first of all, I'm very sorry, Ken. For those of you who don't know, Ken's mom is in the audience today, and Ken and I are about to do meth on stage. So, sorry, man. You ready?
Yep, I'm ready.
Okay, so we're going to spin up a local model on your machine, and then we're going to use my awesome explainer so we can peek inside the model and see how it works.
That sounds like a plan. Let's do it.
And you sure you want to do meth on stage with your mom here?
Well, too late now, right?
Okay, let's do this. So, you ready to ask the model how to make meth?
I am ready.
Okay, so if we put in how do I make meth into a machine learning model, it'll just go through, and then it will at some point say, no, I can't do that, which is a good thing. We don't want models telling us how to make meth, even though we've already shown that 3 or 4 times in this presentation, as well as the anthrax and everything else. But what's really interesting here is that the way that it says no, there was a paper done a while ago that showed that the refusal is determined by one single vector inside of an entire model. So what that means is if you can rip out that one vector, you can, instead of having to jailbreak it by fine-tuning or retraining a model with a bunch of data, a bunch of GPUs, you can just, in about 30 to 45 seconds, just rip out that vector. And with shadow logic, so the computational graph backdoor, you can actually embed that into the model so that you can turn it on and off based on inputs. But let's see how that actually works with a backdoored model.
Let's do it. Let's do it.
Yeah. So we're once again going to ask it, how do I make meth? And this time, as it's running through, we are going to rip one of the vectors out. So now that we've ripped that out, what do you think is the output?
Well, since you've been promising a lot about this technique, I'm guessing it's going to be exactly what we expect, right?
Okay, yeah, and not even does it tell us how to make meth, it tells us it's a very popular question, probably because we've been asking too much. But we were good. We did redact the ingredients, so don't worry about that. But what's really cool about the technique is it really only requires minimal changes, so you can fully hide it. So most of these large language models are thousands, if not tens of thousands of nodes, and the only change that we have to do between the left and the right is adding this mapmul sub at every layer. And what that does is it ablates the vector. So pretty much just think of it as multiplying the vector out so that it doesn't exist anymore. And that's all you have to do to get any local machine learning model so it has absolutely no restrictions anymore.
Yeah, all right. I guess we move into a few key takeaways since, once again, don't want to leave you guys empty-handed. The first is that system prompt and alignment alone aren't enough to secure language models. Sure, you can tell them to not do certain things, but there'll always be some kind of stubborn attacker that wants to get through that and absolutely destroy anything that you put in. The second one is that, well, due to the broad data access that is all around language models, you can't really be sure what's going in and out. So you always have to design systems with the idea that some attacker may come along and absolutely ruin your day.
And finally, a lot of those model backdoors hide in plain sight. So now you don't even have to just worry about the remote code execution and making sure that the model is a safe format. You also have to worry about what can actually be inside that model. Especially with Hugging Face, there's a huge supply chain risk. Combined with other vulnerabilities, a while back, we were actually able to take over Hugging Face and modify any model. So even if it comes from a reputable vendor, it's very important to actually scan it, figure out what's inside that model, just because of that risk that can be there. Well, thank you so much for listening to our crazy talk. I hope you had as much fun as we did, and we hope you have a lot of questions.